Okay, I'm going to do a few of these problems where you need to solve a distance, rate, and time problem with a system of linear equations. And I did a video earlier solving these kind of problems with a one linear equation. So the difference now is that we need to use a system, which means we're going to have two variables and two equations. But we're going to use similar steps to solve these problems. So this problem says two trains leave towns 984 miles apart at the same time and travel toward each other. One train travels 16 miles per hour slower than the other. If they meet in 6 hours, what is the rate of each train? Okay, so just like before, we're going to set up a table that shows rate times time equals distance. That's the distance formula. And then we're going to think about the two trains separately. So we've got a faster train and a slower train. We don't know the speed of either train. In fact, that's what the question is asking for us. What is the rate of each train? So that means our variables are going to stand in for the rate of each train because that is our unknown. So we can use x for the rate of the faster train and y for the rate of the slower train. It doesn't matter which we choose. We're just going to use x and y. Okay, what about the time? It says they meet in 6 hours. They leave at the same time. They meet after 6 hours, so the time is 6 hours. And when we're filling out the table, we want to multiply across to fill in this last column, x times 6, so we'll put 6x for the distance of the faster train, and we'll put 6y for the distance of the slower train. So now we need to figure out what our two equations are going to be. We know we can't make an equation that has to do with the time because all we know about the time is that they both went 6 hours. But the distance has some variables in it, the distance column, and so does the rate column. So what kind of equation can we make about the rate? Let's look at the problem again and see what it tells us about the rate. Here we go. One train travels 16 miles per hour slower than the other. The slower train is the one going slower, obviously. So say train X was going 100 miles, train Y's rate would be 100 minus 16 miles per hour. So X take away 16 should equal Y. Let's make an equation out of that. X minus 16 equals Y. All right, and then our other equation comes from the distance. Now remember, I'm going to make a little picture over here. They started from 984 miles away from each other. Okay, 984 miles is the distance between the two cities. One of them going this way, the other going this way. And one of them's faster, so they definitely didn't go the exact same distance. But they met somewhere in the middle. So by the time they met, this train had gone this far, this train had gone this far. And if we add this distance that the first train went to this distance that the faster train went, the total is 984. So that is our second equation. 6x, the distance of the first train, plus 6y, the distance of the second train, equals the total distance, 984. Okay, so now we've got a system to solve. The directions say you can use the graphing calculator to solve, but I'm going to just solve it by the substitution method. So this equation is already solved for y. Y equals x minus 16. So I'm going to plug x minus 16 in for the y in this equation. That's the substitution method. So 6x plus 6 times x minus 16 equals 984. And then let's distribute 6x plus 6x minus 96 equals 984. Okay, 6x plus 6x is 12x. And then we're going to add 96 to both sides. And we get 12x equals, so 984. My mouse is not working right. There we go. Plus 96 is 1080. 1080 divided by 12 is 90. So that means if we look back at our table, over here, the faster train was going 90 miles per hour. Okay, so 90 miles per hour. Now let's look back at this equation. 90 is x minus 16 equals y. So to find out how fast the slower train was going, we just take 90, subtract 16 from it, and we get y equals 74. So the faster train was going 90 miles per hour, and the slower train was going 74 miles per hour. Okay, this is a good one. This is a problem. They have a few different kinds of these where you've got one thing going against the speed of another. So in this example, we have a motorboat traveling 665 kilometers in 7 hours going upstream, and 500 kilometers in 4 hours going downstream. What is the rate of the boat in still water, and what is the rate of the current? Okay, so in this case, we've got an example where the speed of the boat can be added to the speed of the water when he's motorboating with the current, and the speed of the boat minus the speed of the water when he's going against the current. Some other kinds of problems that you'll see that are kind of like this are like an airplane flying with the wind and an airplane flying against the wind. I saw one that was a child running on a moving sidewalk, and so it was the child's speed plus the sidewalk and the child's speed minus the sidewalk because the sidewalk was moving. So those are all similar, and you're going to solve those all in the same way as what I'm about to show you. So this is a distance problem, so again we're still going to have the rate times time equals distance. Okay, and we're going to have the speed of the boat going with the current, and we're going to have going against the current. So the question is actually asking, what is the rate of the boat in still water, and what is the rate of the current? So our variables aren't going to be in the chart by themselves. We're going to have, I'm going to put them off to the side here. Let's say 6 is the rate of the boat, and y is the rate of the water. So what we need to put in the chart is the boat's rate when he's traveling with the current. So it's the boat rate plus the water rate, x plus y, and then the boat rate minus the water rate. When he's going against the current, he's got the speed of the water working against him, and so that's how we're going to fill in the rate for these kind of problems. The time, when he's traveling upstream means against the current. It takes him 7 hours. So let's put a 7 here. And he goes 665 kilometers. I'm going to put that over here. Oops, I put that in the wrong place because he's going upstream. Oops. Okay. When he's going upstream, he's going against the current. So that goes in the against the current section. So he's going against the current for 7 hours, which means his distance is x minus y times 7. And remember, you need to keep the x minus y in parentheses because those need to be subtracted first before you multiply. And when he is going with the current downstream, he goes for 4 hours. So that is going to be 4 times x plus y for going with the current, which is downstream. Now we know the distance upstream is 665 kilometers. And we know the distance upstream is 7 times x minus y. That means those two quantities are equal, so that gives us an equation. 7 times x minus y equals 665. And likewise, we know when he's going downstream, he goes 500 kilometers. And we know when he goes downstream, he's going 4 times x plus y kilometers. So those two are equal, and that's our second equation. 4 times x plus y equals 500. Okay, and it says you can use the graphing calculator to solve this, but we're going to solve it the normal way. We've got 7x minus 7y equals 665, 4x minus 4 or plus 4y equals 500. Now to do the substitution method, we're going to need to solve one of these for one of the variables. So I'm just going to solve this one for x, not for any particular reason. That's just the way I decided to do it. So 4x equals 500 minus 4y. Then we need to divide everything by 4 to get x by itself. So x equals 500 divided by 4 is 125. 4y divided by 4 is just 1, so it's 125 minus 1y, or just minus y. So we're going to take 125 minus y, which equals x, and we're going to plug it in for x in this other equation over here. So 7 times 125 minus y minus 7y equals 665. 7 times 125 is 875 minus 7y minus 7y equals 665. So 875 minus 14y, negative 7y, and negative 7y is negative 14y equals 665. Now I'm going to subtract 875 from both sides. So 665 minus 875 is negative 210. On the left side we have negative 14y. So we want to divide both sides by negative 14. And we get 15. Y equals 15. And if we look back at the notes we made over here, y is the rate of the water. So now we know that the water is going 15 kilometers per hour. And we can plug that into one of our other equations to find out how fast the boat is going. And this equation is nice and simple, so let's plug it in here. X equals 125 minus y, which is 15. 125 minus 15 is 110. So that means the boat is going 110 kilometers per hour. Now remember, this is kilometers per hour, not miles per hour, so these numbers are actually reasonable. All right, that's it.